evening session of the school, and the keynote speaker of today is Professor Nicola Spaldin from the University of Santa Barbara, that will talk about a very broad subject, how to use density functional theory to design new materials and understand everything.
So just two specific things, nanoelectronics and the origin of the universe. So it's nice to see you all, or to hear you all still kind of chatting and laughing. I thought by this time in the week everybody would be kind of totally had their brains fried. When Sinead worked with us last summer, and when she left, she bought us a bottle of toasted head wine, and she had this image of you all with your heads toasted by now. There's not going to be a single technical thing in this talk. I figured you had enough instruction in the technicalities of density functional theory already this week. So I'm going to talk about what we do in my group, which is to use density functional theory as a tool to design new materials. And I'm going to show you two specific examples that we've been playing with. One which is which potentially has applications in electronics, and the other one is to try to distinguish between various extensions to the standard model in high energy physics, again using density functional theory to design new materials. And these are kind of ongoing long-term projects which will be showing you results from many collaborators, some of which are group members, past and present, and many of whom are shown here. I usually show this photograph to kind of show off that we live on the beach here in this beautiful place, but you all know that already. We're a little unusual for a research group in the United States in that we don't take any defense or industry funding as a matter of principle. So I'm tremendously grateful, and we would rely very much on the National Science Foundation, and all our funding comes from their various different programs.
Is this your own policy or the university's policy?
Oh no, it's my own policy. I think we're probably the only group in engineering who doesn't do that. Watercone also does not, but he's from a generation where it was perhaps less of an issue. We're considered to be a little bit mad. Okay, so here's what I'm going to do. I'm going to tell you about the kind of procedure that we follow when we go about designing a new material with a specific functionality. And I need to mention a little bit some kind of non-standard DFT, just very briefly, that's going to be relevant for the particular materials I'm going to talk about. And the two case studies that I'm going to discuss belong to the broad class of materials that combine both magnetic ordering and ferroelectricity. And so I'm going to talk about controlling magnetic properties with an electric field. That will be the first one, and then the origin of the universe. I think that next week you're going to hear from Warren Pickett, who's going to give one of the keynote lectures. Got a little chopped off on the bottom here. About 6 years ago now, Warren and I sat down and tried to kind of make a flow chart of how we go about thinking about designing new materials. Warren was also at the time trying to make new half-metallic anti-ferromagnets at the same time as we were thinking about how to design new magnetic ferroelectrics. And this is kind of the flow chart, I guess, that we came up with, that we follow in our procedure. And obviously nothing fits exactly into this scheme, but this broadly is how we go about doing things. So the first thing that you have to do, which seems like it's kind of obvious and barely worth writing down, is you have to identify what functions you want to put in your material. And this one, I think, is actually kind of profound. How many of you students wake up in the middle of the night with panic attacks thinking, when I get my own position, how on earth am I going to know what to work on? Anybody? I used to do that for 3 or 4 years, I remember, thinking, I'm never going to know. Like, how do these professors know what to do, right? So this all comes into this first question. What are you going to work on when somebody gives you your faculty position and your startup funding, and you're told, okay, go away and design new materials? You have to think about what do you want your materials to do. So maybe think about that. Another quiz later on. You can think about it. If you could design as a bright young new person with no constraints and your whole career ahead of you, what material do you want to make with your time? So that's the first box. So for us, we decided we wanted to make materials that were magnetic and ferroelectric. I'll tell you a little bit about why later. But you may want to make materials that absorb sunlight and drive your car or something, or some combination of things. Once you decide what you want to do, then you have to understand the physics and the chemistry that causes those functionalities. And here's one place that we use density functional theory, and I'll give you an example of how we can use our computational methods to help us understand what makes things do what they do. Then the next step is kind of the magic trick. We've decided what we want to do. We understand how materials that exist do that to the extent it can be understood. And now we have to guess arrangements and types of atoms that we think will have the properties that we're looking for. Okay, so this is a little bit of a kind of solid state chemist's black art. We're going to say, well, we think if we put our atoms here, they might do what we want. And there's no real density functional theory, I'd say, in this step. The density functional theory comes in the next step, where we take our arrangement of atoms, and using the tools that you're learning about this week and next, we go away, calculate the structure that those atoms want to have. We're using the Hellman-Feynman forces method that Shobana talked about on the second day, I guess. And then once we know where the atoms want to sit, we can compute the properties. Okay. At the same time, or sometimes somewhat afterwards, we go persuade our experimental colleagues to also make these materials and measure the properties. And if things work out as we hope, then the properties we compute come out being the same as the properties we measure. And as you can imagine, this is not always the case, and sometimes this is because our theoretical methods were not appropriate. More often, I'd say, it's because the experimenters didn't put the atoms in the right place. And so we have to go and persuade them to improve their synthesis method. Or they put in extra atoms. They put in defects that we didn't put in the computer. But eventually, with enough iterations around this loop, we might expect the computed and the measured properties to be the same. And again, if things work well, the properties we measure are those that we want, and we end up with our rationally designed new material. Again, this doesn't always happen. Even if we have our atoms where we wanted to put them, sometimes the properties those atoms have aren't what we expected. Then we have to go back and rethink, what causes that property after all? Maybe we didn't understand that well enough at the start. So this is our scheme that I'm going to be following for the two examples that I'm going to show you. So any volunteers for what you want to put in your designer material when you have your faculty position and your pot of startup money? Nobody? Nobody have somebody must have like doesn't anybody want to do like a room temperature superconductor or something at least? No? We need to do some vision training. It's an important question, what do you want to do with these fantastic skills you're learning? Think of something. Okay, so I briefly wanted to mention something that I think is going to be discussed tomorrow about actually, this is a little bit slides gratuitous. I put it in because I think Walter looks so dashing getting his Nobel Prize from the thing this week. But we know that density functional theory, in principle, allows us to calculate all the ground state properties. The ones that are going to be particularly relevant for me tonight are magnetic ordering and these ferroelectric properties, ferroelectric polarization and dielectric and piezoelectric response. But I just wanted to remind you that we need to have a reasonable approximation for the exchange correlation functional. And the materials that I'm going to be talking about are all magnetic, so they're rather strongly correlated, and they're all insulators, so they're magnetic and insulators, which this combination makes them rather strongly correlated. And so the kind of more conventional exchange correlation functions, the LDA and the GGA, are generally not appropriate. They don't give us good results. Often they'll give us metals. And for ferroelectrics, materials with a spontaneous electric polarization, these have to be insulating. Otherwise, when you apply an electric field, you'll get a spontaneous current rather than a spontaneous polarization. And so LDA and GJ often will give us metallic behavior. And so we need to use some kind of extension, some kind of beyond LDA method, and occasionally some kind of beyond DFT method, like dynamical mean field. I think that all the results I'm going to show you tonight have been obtained with the LDA plus U method. I'll try and remember to point out if I show you any others. So remember that, depending on what kind of material you want to make, you have to be somewhat careful with the kind of density functional theory that you need to do. And that's all I wanted to say about kind of the technique side. Everything else that I could add, that I could say, I would say less well than you're hearing about during the day in the next couple of weeks.
So when you LDA plus U, how do you choose U? You choose U in
that's a really good question. I wonder is that something that's going to be discussed? If you can hear the question back, the question was in the LDA plus U, how do you choose the U? Who's talking about LDA plus U tomorrow? tomorrow.
Tomorrow, yeah.
Are you planning to cover that?
Yeah.
Okay. I think maybe we save it till tomorrow because it's such a profound question, which I could talk about, all night. What we tend to do in my group is we use U as a variable, and we vary it over a range of physically likely physical values. And if the qualitative physics doesn't change over that range, then we go and have a beer and say then we're good.
But the calculation could be very time consuming, right? I mean, if you choose all the U, right?
Well, that's not terrible. We go say U from 0, where the LDA, through 10 electron volts. That's completely the range you need to span that for any realistic material. And if many materials, there's no qualitative change over that range. Sometimes you get unlucky and there's something like a spin state transition right in the middle of the likely range of U values, and then you're really in trouble. And it's not clear to me in those kinds of cases that LDA plus U is the best tool to be used. I think you'll hear tomorrow about the kinds of self-consistent ways of generating the U that Mateos and his colleagues developed. So I'll leave that question. A very good question. Any other questions before I go on? Anyone thought of their dream material yet? No one. You're not allowed to go home until someone.
Beer. Liquid material.
Liquid materials. That's been done. What specific new functionality?
Well, there are many of them. Not particularly new.
You do not get drunk.
Well known.
Okay. So I want to make a material, and again, I'll tell you why in a minute. But I decided I wanted to make a material where I could control the magnetism with an electric field. So normally, if you have properties like electric polarization or dielectric response, you control those electrical properties with an electric field. And likewise, if you have, say, magnetic data bits, you have regions of magnetization in your hard drive that you want to switch, you do that with a magnetic field. Okay, so these electric field and magnetic field are the conjugate fields for electric polarization and magnetization. And what we want to do instead is to modify the magnetic behavior with an electric field and reciprocally the electric polarization with the magnetic field. And these kind of cross-coupling terms here are referred to as the magnetoelectric response of materials. And the reason that I got interested in this actually is because it's really hard to do. It's a very interesting research problem to control an order parameter with a field other than the conjugate field for that order parameter. There are also technological reasons, which are kind of a nice side effect. And what the kind of sales pitch for magnetoelectric materials is that if one could do all of the current magnetic technologies, such as magnetic data storage, but do the control of those using electric fields, this would offer numerous advantages. At the moment, if you want to switch your data bit in your hard drive, you have a magnetic field in there to do it. And your magnetic field is generated by a coil of wire. And that's bulky, it's heavy, and it gets very hot. And so an electric field, you just need a couple of electrodes. It's very light, it's very low power, and we don't need any cooling. So the kind of main technological driver in this little schematic we just looked at is to do this direction, to be able to, with an electric field, control the magnetic properties. There are a whole bunch of kind of more mundane applications. If we could just get to combine electric polarization and magnetization in a material, we could do things like have an antenna where we had just one component, could be the inductor and the capacitor, for example. But these kind of coupling responses are the most fun. So this is why we want to do it. And these materials with magnetoelectric response belong in a kind of broader class of materials which are known as multiferroics that combine, in which some combination of the ferroelectricity that we've been talking about, electric field control of electric polarization, and ferromagnetism, magnetic field control of magnetization, and also ferroelasticity, strain control of deformation coexist. And you can see this schematic I had earlier is kind of this part of this triangle turned on its side. We want to be able to combine the properties of ferromagnets and ferroelectricity in the same material so that we can have this coupling, this magnetoelectric response. This is a rather fashionable area. For the last few years, every time this is the search, if you do a search on Web of Science, I think the search is actually for the search term is magnetoelectric. This is the number of publications per year over the last 20 years. And you can see that when I first got interested in this about 10 years ago, it was kind of there weren't so many people to talk to. I think there was about 10 publications per year in this field. And things have really started to take off, and it's been increasing exponentially for quite some time now. So there's rather a lot of activity, in large part because synthetic techniques, many of the materials I'm going to talk about are being made in thin film form, and techniques for doing thin film growth of oxides have really taken off. So we now have rather good materials that have in turn led to the development of new physics. And it's just a little bit out of date now. A year and a half ago, this was the most interesting problem in all of material science, and not just because I thought it was, but Science magazine at the end of every year publishes a list of the most interesting problems in all of science. And there were 10 topics chosen at the end of 2007, and one of them was multiferroics, and it was the only one, in fact, in material science. Other ones were personalized human genomics was one, and the onset of the Large Hadron Collider, and multiferroics was up there with those. I'm not quite sure who makes these choices, but it's official that it is actually the most interesting problem. Okay. So where should we start looking for multiferroics? We've decided the functionalities that we want there. Now we have to choose our arrangement of atoms, what kind of atoms are going to be appropriate. And most, if not all, almost all of the work that's been done in this area so far has been in oxide-based materials, and mostly transition metal oxides. And there are a number of reasons for this, both practical and physics-based. How many of you work on oxides? About a quarter of you. Why do the rest of you not? By the end of this talk, you'll be really bummed that you don't work on oxides. This is a plot of the abundance of the atoms, of the elements in the Earth's crust as a function of the atomic number. And anything greater than 1, or anything less than 1, is considered to really be a problem. So those of you who work on 3-5s, you're totally in trouble because you're going to run out of indium soon. Indium's pretty bad. Selenium, so a lot of the group 4, the group 6 compounds, selenium are pretty low down here. Oxygen is the most abundant element in the Earth's crust, and so it's obviously favorable from the point of view of not running out. It's oxides tend to be non-toxic. They're stable to oxidation, usually, unless you get some very strange oxidation state. And the kinds of oxides we're going to be looking at are oxides of transition metals, which are kind of this region here, and they're also fairly abundant and pretty benign. So from a practical point of view, it makes sense to be looking for oxides for new technology. From a physics point of view, oxygen is it's a very special place in the periodic table. The polarizability of oxygen in an oxide is just right, or the kind of bonding that oxygen makes in an oxide is just right to give it a kind of perfect polarizability in an electric field. If you go to the left of oxygen to the nitrides are very covalent, and so they're boring. If you go to the right of oxygen to the fluorides are really ionic, and they're also boring. But oxygen is right in that intermediate region where it's very responsive to an electric field, and so it's extremely interesting and extremely functional. You get a lot of functionality in oxides. Many atoms form compounds with oxides. The chemistries are very diverse, and many structures can be formed with many dimensionalities. And the fact that we're going to be making compounds of oxygen with transition metals gives us this extremely important physics I mentioned already of strong correlations, in which the behavior of one electron explicitly influences the others. Now, this, of course, is exciting for functionality. It can be a little bit of a problem for density functional theory, because you're using a mean field method, and so explicit correlations are rather difficult to include. But the kind of functionalities that result from these strong correlations are, for example, high temperature superconductivity, colossal magnetoresistance, unconventional magnetism, and the multiferroism that we're going to be talking about. Okay. So we've chosen the functionalities then that we want to include. I've given you a little bit of motivation that we're going to start looking in the kind of chemistry region. We're going to be looking in oxides. So what I want to talk about next, very briefly, is what kinds of chemistries give us ferroelectric compounds and what kinds of chemistries give us magnetic compounds. Because these tend to not coexist together, and we need to understand why in order to make some trial compounds. Any questions before I go on? So this is going to be your kind of 5-minute introduction to ferroelectricity. For those of you for whom this is unfamiliar, it'll probably go a little bit too fast, and for those of you who know all about ferroelectrics, it'll be a review. This is a picture of the perovskite structure, which is the prototypical, the structure adopted by prototypical ferroelectrics, and it consists of a transition metal cation surrounded by a cage, an octahedron of oxygen anions, with another cation at the unit cell corners. And so an example would be barium titanate, barium titanium 03. And what happens in the ferroelectric phase is that this positive titanium ion moves away from the center of its cage of oxygen anions, so it shifts like this. And when it does that, it makes a dipole moment, because the pluses and minuses in the unit cell are no longer equally spaced. So this is what makes ferroelectrics be ferroelectric, that this atom moves away from the middle of the cage, and now I have a plus closer to a minus atom with dipole. And experimentally, it's known, or one can just look at all the data, and one finds that this off-centering only occurs for transition metal cations that have empty D manifolds. So we call those D0 cations. So for example, titanium 4+ off-centers, manganese 3+ that has D electrons sitting on it does not. It stays in the middle. So this is just an experimental fact. So going back to our flowchart again of understanding the chemistry driving the functionalities, we have this experimental observation and we want to know why it is. And here we can use our density functional theory because we can go look at barium titanate when it's ferroelectric or when it's not. We can push in the computer that titanium back to the middle and see what changes in the forces and the charge density. We can take a magnetic perovskite that in real life is not ferroelectric, where the magnetic ion doesn't move off center, and in the computer we can move it. We can control complete, we have complete atomic control, and we have complete characterization because we can look exactly at what the electrons do when we do that. And so we can use our density functional theory to understand this observation. And what we find is that this off-centering has an energetically unfavorable component because the Coulomb repulsion between the electrons wants to push it back. And this Coulomb repulsion, this energetically unfavorable component, is particularly large if the d orbitals are filled or partially filled. It has an energetically favorable component, which I've tried to sketch here, in which covalent bond formation occurs between the oxygen and the cation. And the covalent bond formation can only occur when you have empty d orbitals. Because the oxygen orbitals are already filled, the d orbitals have to be empty for this bond formation process to occur. And let me show you how this looks actually in the output from a density functional calculation. And I've chosen to show you the calculated density of states, not band structure. One also can see this if you look at the changes in the charge density. If you look at the Vanier functions, you can see this same behavior. Here's on the left barium titanate, which is a D0 titanium cation. It is a ferroelectric experimentally and in the computer. And on the right, here's calcium manganite, which has partially occupied d orbitals on the manganese. It's not a ferroelectric either in real life or within a density functional calculation. But what we've done here in the top, we've put the titanium ion in the center of its cage, and which is kind of artificial. It doesn't want to do this. It wants to move off center. And we've put the manganese ion in the center of its cage. And in the bottom, we've allowed the titanium to displace, and we've artificially displaced the manganese where it doesn't want to. So the kind of real experimental situations are this one down here and this one up here, but we've made these artificial situations in our computer. And what I want you to notice here is in the barium titanate case, where we have a very small Coulomb repulsion, we get very good chemical bond formation. So look at where the bottom of the valence band is. In the centrosymmetric state, it's at like -4 electron volts. When we allow the titanium to move off and become ferroelectric, it shifts down a couple of electron volts, and we have this large overlap in the density of states, indicating bond formation. If I showed you instead the charge density, we'd see this pile-up of charge density between the titanium and the oxygen, showing us the covalent bond. You can't see from this plot that we have also small Coulomb terms. And then over here, when I do the same thing and push my manganese off-center, I don't get this nice bond formation. There's more or less no change in the density of states. If I were to look at the charge density, I wouldn't see this nice build-up of charge density between the bonds. So this is the kinds of things we can do with density functional theory to try to understand existing behaviors. These were LDA calculations, by the way. These are rather, you can't see because it's got chopped off. These were rather old, 2002 calculations, right at the start of this story. I'm not going to, in the interest of time, I'm not going to discuss what causes magnetism. I'm going to tell you that, for those of you who have not studied a lot of magnetism, that to be magnetic, one needs rather localized electrons, and the usual source of localized electrons comes from d electrons on the transition metals and transition metal oxides. So those of you who, actually most of you are still awake, or you're sleeping with your eyes open, will realize we're in trouble. We've just argued that to be ferroelectric, we need to not have electrons in the d orbitals. To be magnetic, we must have electrons in the d orbitals. And if you want to read more about this is a photograph of the beach in Sweden, sent to me by a woman, a researcher at University College, at Imperial College London, and this is my book called Magnetic Materials that she was reading on her summer vacation, and it discusses a lot about why one needs localized electrons to be magnetic. I'm stalling for time here, so you can write down the ISBN number if you'd like to do that. You can see it's a good summertime reading. Actually, she's not so far through it.
But only in Sweden.
Only in Sweden.
Where summers are rather cool. But
they're also rather short. Where she's investing a big percentage. This could have been the only sunny day. So magnetism and ferroelectricity then are chemically contraindicated. To be magnetic, we need to have d electrons. To be ferroelectric, we need to not have d electrons. So what are we going to do? Any ideas? Apart from Andre, he's not allowed to answer because he works on multi-ferrites too. Any ideas? So we've made an argument that this cation, if I make it magnetic, it's not going to move off center. If I want it to be ferroelectric, it has to be not magnetic.
Have two types of cations?
Exactly. And we already have two types of cations, right? In this perovskite structure. This guy in the corner here is also a cation. So why not make one of these be the magnetic one and the other one be the one that's going to off center? So this was actually one of the choices, and it's the one I'm going to show you. There are many other possibilities, and I don't know, in the poster session, are you going to show your terbium manganite work? Yeah, so Andre will show work where actually the arrangement of the magnetic ions is chosen such that it becomes polar. So the actual magnetic arrangement, I think you're going to hear about non-collinear magnetism tomorrow. It's possible to have a non-collinear magnetic ground state that's polar, and then that causes a ferroelectric distortion. So that's another possibility. You can go to Andre's poster to see that. But we're going to do this kind of more straightforward route of letting this ion be magnetic and make this one be ferroelectric. At least for the first project that I'm going to show you. When we do the origin of the universe later, I'm going to do it the other way around. Make this one be, well, you'll see. Origin of the universe is a bit harder. Okay. So remember, so this one's going to be magnetic, the one in the middle of the oxygens, and this one we're going to make off-center. So here's our kind of this was really our first kind of designer multiferroic. And I don't want to oversell kind of what we did here. Bismuth ferrite as a compound was known to exist. It was known to be, or it was believed to be antiferromagnetic. It was kind of thrown around a little bit that maybe it was ferroelectric, but it was believed to have an extremely tiny polarization. So we didn't make an enormous leap out of nowhere to decide to study this compound. So bismuth ferrite is again a perovskite structure. The iron is the one surrounded by the oxygens, and that's magnetic, so it's not going to off-center. It's got d electrons. The bismuth, the reason that we have the bismuth in there is because bismuth 3+ has what's called a stereochemically active lone pair of electrons. It has a spare pair of 6s electrons sitting on it that aren't really involved in the binding. And they fill space in just the same way as that spare pair of electrons on the nitrogen does in ammonia. So remember in your introductory chemistry class you learned why NH3 is not planar, why it's trigonal pyramidal, or I think it's called, rather than planar, because of this lone pair of electrons. And this is also why it has a dipole moment. The lone pair of electrons is negative, the hydrogens are positive, so NH3 has a dipole moment. So this is what we were hoping for the bismuth in bismuth ferrite, and the magnetism is coming from the iron 3+. And what we found when we made this calculation, we put all the atoms in the computer and optimized the structure and then calculated the polarization using the Berry phase method. Have you talked about that yet? Is it coming? Next week?
Not sure.
Not sure? Okay. Friday. So maybe you'll learn about how to calculate polarization soon. This is the structure that we calculated. So the black dots here are the bismuth atoms, and these little umbrellas, this is the calculated charge density, these little umbrellas, yellow umbrellas, are the lone pairs. And so you can see we have negative lone pair, positive bismuth ion, negative lone pair, positive bismuth ion. We have these beautiful dipole moments lining up through the structure. And the calculated polarization is huge, 90 microcoulombs per square centimeter. This is larger than the best known, previously best known ferroelectric materials. As I said, this material existed previously, but was believed to have a very small ferroelectric polarization. When we had modern films made using pulsed laser deposition and high quality films and had modern ferroelectric measurements done on them, we also obtained a measured polarization of 90 microcoulombs per square centimeter. So ferroelectric polarization is actually one of the properties that density functional theory can predict extremely well. It's a function, it's entirely a ground state property. And again, provided that one has a good exchange correlation functional, we get extremely accurate answers for ferroelectric polarization. It turns out that it's a rather difficult experiment to do. And so it's, I think, a field where first principles calculations are really ahead of experiments. And so what I've seen certainly in the examples of multiferroics is that the calculated value becomes the definitive value, and the experimentalists kind of fluster about and eventually converge on that value as they improve the properties of their samples. The problem is if you have any leakage in your sample, you get leakage current adding to the kind of the polarization current. And so it's a difficult experiment to do.
This number 90 experimentally extracted from single crystal?
From single crystalline films. The problem with bulk single crystals is because this number is so large, and because there's an elastic distortion associated with the ferroelectric polarization, it's very difficult to completely switch them in the other direction, the electric field. And so I believe that very recently, switching experiments have been done on bulk single crystals, but they're very, very hard to do. They have to be, the fields you need to switch have to be so large because the polarization is already so large in one direction that you need extremely perfect crystals with no defects. So this measurement is for a thin film, a single crystalline thin film, not a bulk.
So when you design this kind of new material in the domain of density functional theory, another new thing is going to come like magnetoelastic effect. Can you incorporate that within the framework of density function?
We can, and I think tomorrow you're going to learn about spin-orbit coupling. Is that right? Yeah. So in order to have coupling of the magnetism to the lattice, you need to include spin-orbit coupling in the calculation, which is again a little bit non-standard, but you'll learn about that tomorrow. Okay. Other questions? Okay, so this is good. This is a huge ferroelectric polarization. The problem, though, is that the magnetic moments on the iron ions actually anti-align. So in terms of getting a material with a net ferroelectric polarization and a net magnetization, we're only halfway there. We have a very large ferroelectric polarization, but we have an anti-alignment of the iron ions. In the interest of time, I'm not going to tell you about it. The second thing that we tried, we've got exactly the opposite. We've got a ferromagnetic alignment of the moments, and we've got anti-parallel alignments of the lone pairs. So it's a tricky problem.
So does that value depends on the thickness of the thin film?
The polarization or
The polarization? In fact, if you grow very thick film, usually the polarization will die away, right? The ferroelectricity will die away, right?
In a very, very thin film, you end up with a problem because you have positive charge on the top and negative charge on the bottom, and that provides a field in the opposite direction, which is called the depolarizing field. And if your electrodes are not able to completely screen that, then it can unpolarize the ferroelectric. And the details of if or how that happens are, I'd say, a current research question for all ferroelectrics, not just for bismuth ferrite. Yeah. So that's a good question.
Could you explain more about how lone pair is related to ferroelectricity in bismuth ferrite?
So the lone pair, I think, at this kind of simple level, the lone pair is negatively charged, and the ion it's attached to is a positive cation, and so it introduces it's a dipole. Or if you like, you can think of it that the ion ends up off-centered because this charge fills some space. If you prefer to think of it that way, the electrons are occupying some space, so it pushes the ion away from the center of its cage. Kind of like the titanium moving off-center in the barium titanate, the bismuth's moving off-center in the bismuth ferrite.
So isn't it related to bonding nearest to oxygen?
Somewhat. So if you analyze, in fact, the kind of if you look at in a Vanier representation, the behavior of the bands associated with this lone pair, they actually have quite a lot of oxygen content. So they're not just bismuth based, and that's another I'd say active research area is why some lone pairs of electrons are active like this, and some just sit there being spherical. So, for example, lead telluride has a lone pair just sits there being spherical. Germanium telluride off-centers like this. And I think the details are not understood. Other questions? Okay.
So when this kind of material comes into real application, they usually go in the polycrystalline material. It's not always possible to make a real application with highly semi-crystalline. It's very expensive, as you know. Most of the applications they are for polycrystalline. Now, when you really arrest the material in the polycrystalline phase, this number is going to change very drastically.
Okay, so the question was, how does this number change in a polycrystal? And, I should kind of issue a disclaimer of academic immunity that I'm not at all an expert in ferroelectric devices, but my understanding is that polycrystalline, for example, lead zirconium titanate, which is used in a lot of piezoelectric applications, once you apply an electric field and kind of line it all up, there's not a large drop in polarization. There's a little bit of a kind of cosine theta if your grains are not all exactly aligned, but I don't know that there's much beyond that. I don't know, is anybody, do we have any ferroelectrics experts? I should probably, I can pontificate, but I can't give you any insight, I think. But certainly, this is always, these are, our calculations are never for polycrystals, obviously. Along these lines, though, Fujitsu in 2006 proposed that they plan to use bismuth ferrite for their next generation ferroelectric memories, not at all because of its being multiferroic, entirely because it has this very large electrical polarization. So, so maybe one shouldn't worry too much if you don't end up with exactly what you're looking for, as long as it does something useful. Because they've not actually, I think, released a memory with bismuth ferrite in their export. The bismuth ferrite, bismuth-based ferroelectrics have the advantage, of course, also that they're lead-free, which is a big driver in the European Union. Is it since 2006 that all microelectronics is supposed to have been lead-free? And I think there's been an exemption specifically for piezoelectrics because lead was so prevalent in piezoelectric materials. But that will, run out eventually. Okay. Another kind of recent discovery that we made in bismuth ferrite, which is rather interesting and may or may not be related to the fact that it's multiferroic, is that the domain walls conduct. So this picture is showing, in the middle here, the ferroelectric polarization is pointing out of the plane, and in this region it's pointing into the plane, and this kind of bright spot here is the domain wall, and the reason it's bright is because we're scanning across, we're scanning the conductance across the film, and the domain walls conduct. And this doesn't happen in conventional ferroelectrics, and we've been doing density functional calculations to try to understand why. I'm not sure that we've been really successful in our understanding, but it's another rather interesting behavior that we hadn't anticipated. Okay, how's everybody doing? Everybody awake? Anybody thought of their, Stefano's asleep, this is bad. Yeah. Anybody thought of their ideal material yet, apart from beer? What you want to make in your ideal material? Okay, so here we are in our plot. We made our trial compound, we calculated, we made it. What we got was, what we calculated was what we made, eventually after a few iterations on the synthesis side, but it wasn't what we wanted. We got a good ferroelectric, but it didn't turn out to be magnetic. So we have to kind of go back up here and think some more about what makes ferroelectrics be ferroelectric and what makes magnets be magnetic. And the specific thing we want to fix is the fact that our bismuth ferrite doesn't have any net magnetization, that it came out to be an anti-ferromagnet. We want to have overall a net magnetization. So I'm going to go through this super quickly because I want to show you the origin of the universe. Here's what we decided to do. When we thought about it, we noticed, or it was kind of widely known, that in an insulating oxide, the magnetic moments are actually usually anti-aligned. They tend to want to go anti-parallel. And again, you should find my book to find out why, or download it for free from Google Books. So what we thought was, well, let's make a ferrimagnetic ferroelectric. So we'll give up on trying to align the magnetic moments parallel. We'll accept the fact they want to anti-align, but we'll make half of them have bigger moments than the other half, so that they don't end up completely cancelling out. So we went back to our density functional calculations, and we made the same kind of material, but we put in two different transition metals, iron and chromium. And iron has 5d electrons and chromium has 3d electrons. And what often happens in these so-called double perovskites is that the two different ions will form kind of a checkerboard, like I've shown here. So we tried different arrangements. We made supercells and tried different arrangements. And indeed, we found that they form this kind of checkerboard. And that they really do want to align ferrimagnetically. So we obtained a moment of 2 Bohr magnetons per unit cell. We kept the large spontaneous polarization. We then went and calculated the strength of the magnetic interactions from our density functional calculations, and then did a mean field calculation for finite temperature. And what we found, which we were a little bit disappointed about, was that the Curie temperature was around 100 Kelvin. So when we plotted magnetization as a function of temperature, it went away actually about 130 Kelvin in our calculation. So this is obviously not a density functional calculation. This is a finite temperature calculation using input from density functional. So this is now all in the computer. We then went and had it made, and getting it made took a while. So this turned out to be a very difficult synthesis to do. There were a number of attempts using high pressure techniques, in thin films using pulsed laser deposition. The Mexico group made a powder, which I was very excited, they called it La Nicolita, but it didn't work. None of these managed to obtain the kind of double perovskite ordering that we needed. And actually just last year, the group of Masaki Azuma in Japan, using thin film techniques, was able to do the appropriate arrangement of the atoms with the correct layer-by-layer growth. The downside is they can only do 5 unit cells, and then they start to get mixing. So they're only able to stabilize 5 layers in this structure. And what they find is very exciting from a practical point of view, or at least it would be if they could do more than 5 layers. This is the measured magnetization as a function of magnetic field. The blue is this new compound, and these smaller curves down here are just bismuth ferrite or bismuth chromite, so this is kind of their noise limit. So they see magnetization, but it's at room temperature, so it's better than what we predicted, so we're not complaining, but it's certainly not what we were expecting. And here they do find that they have a ferroelectric polarization. They don't have magnitudes. They don't have enough material to get magnitude. But what they do here is they apply, within the big square, first they apply a down electric field. Then within the little square, they apply an up electric field. And then they come in with a piezo force microscope to measure the contrast. And so you can see that they have different piezo response in these two regions. So it seems to be a room temperature ferroelectric, which is very exciting, and in fact it's doing really better than we were obtaining in our calculations. So that's the end of this section. Hopefully I've given you a little bit of an example of how we're able to use the tools that you're learning this week, both in understanding and in predicting new multifunctional behavior in materials. There was a nice editorial in Nature Nano last year that accompanied an article actually on a different multi-heroic that we made about how theory and experiment have now kind of converged in length scale. The kinds of calculations that we can do are kind of at a higher length scale now, and the kinds of experiments that can be done are down at a smaller length scale. So we can really have a productive interplay between the two. And I think a room temperature multiferroic is probably not unachievable, but it's very, very hard. It's not an easy problem. Maybe a less difficult problem than a room temperature superconductor. Maybe a less useful problem. How are you doing for energy? Do you want to go for a beer, or do you want to know about the origin of the universe?
Origin of the universe.
Origin of the universe.
Then we will enjoy better the beer.
Yeah. So I got involved in this project. Well, let me tell you about it. Our idea is to measure the dipole moment of the electron. And the dipole moment of the electron, just a free electron, is very small. For all practical purposes, it's zero. As a material scientist, 10 to the minus 27 electron centimeters is a zero dipole moment. The fact that this number isn't known to be exactly zero by experiment, but if you're a high energy physicist, this is an extremely significant number, because various extensions to the standard model, such as supersymmetry, grand unification, multi-Higgs, all predict different values for the dipole moment of the electron. And those values are all around 10 to the minus 29 electron centimeters. So if one could improve the experimental resolution of the measurement of the electron dipole moment by 2 orders of magnitude, one could distinguish between these extensions of the standard model, because multi-Higgs might predict a number that's now too large to be consistent with experiment. Question?
How does the electron have a dipole moment?
Well, basically, it doesn't to a normal physicist. It only does to a high energy physicist, right? So basically, I guess what it means is the distribution of the electron cloud is non-symmetrical by an amount of the order of 10 to the minus 27 electron centimeters. Yeah, so it's like a balloon that's not quite spherical. But it's,
Not sure that these pictorial views.
Yeah, because there's not a cation on there.
So what's the magnetic moment of an electron? It's not linked to any physical picture. It's just there.
Yeah, but I guess we're kind of just more used to accepting the fact that an electron has a magnetic moment than a dipole moment, right? I mean, it's all negative, so how can it have a dipole moment? So if this bothers you, unless you want to go into high energy physics, you could just, it really doesn't matter. To a material scientist, this number is zero. Yeah. And so the reason I got involved in this project is because there has been a proposal to do a solid state experiment to measure the dipole moment of the electron. And the details of the experiment and why they think they're now able to reduce the accuracy, the current measurements are all done optically, why this one is able to give an accuracy of 10 to the minus 29, I can't reproduce for you. There are some papers which I read through and seemed not implausible, but I didn't understand them well enough to be able to reproduce. But what they need in order to be able to do this experiment, which basically consists of a magnetoelectric switching experiment at liquid helium temperature, is they need a low temperature multiferroic. So this group came to me and said, what we want is a ferroelectric. We want to work at liquid helium temperature, so we need to be able to switch the polarization at a few Kelvin. But we'd like the polarization to be as large as possible, and we want the dipole moment in the ferroelectric to be around the magnetic atom. So when I switch my polarization, the environment around the magnetic atom has to change a lot. They want it to be magnetic, but they need the magnetism to have not ordered when they get down to liquid helium temperature. It has to stay disordered magnetically. And they need a bulk sample. So the bismuth ion chromite, for example, where we only have 4 or 5 atomic layers, is no good. So these were the constraints in order to be able to do this experiment. And initially I said, oh, no problem, we've been failing for 10 years to get a high temperature multiferroic. I'm sure we can make you a low temperature one. But actually, well, I guess this has turned out to be a little easier because we have done it. But
can you tell us what is the physical principle that would allow them to measure such a tiny effect?
Why they're able to back out? Well, so they do basically electric switching around a magnetic site, but what I can't explain to you is why they think they're able to back out all the other magnetoelectric contributions to isolate that coming from the electron dipole moment. But I can certainly share the papers with you, but I can't reproduce the argument. As I say, it seemed not implausible, or it seemed plausible enough when I read it for me to want to invest my time in trying to make this material, but I can't reproduce the explanation. Okay. So here was the plan that we came up with. Again, going back to kind of step 2 in the flow chart of how do I decide where to arrange my atoms. We thought about this for a while, and we realized that, so we talked about barium titanate as the prototypical ferroelectric. It's a very good ferroelectric. It's not magnetic. There's nothing magnetic in barium titanate. And this lower observation is going to be relevant in a second. It has a rather large lattice constant. Europium titanate is rather an interesting material. Europium is the only rare earth that goes divalent. It's 2+, just like barium, and so the titanium is 4+. It's not a ferroelectric, though, in spite of having D0 titanium 4+. But it is magnetic because of the F electrons on the europium. It's magnetic with already a rather low Néel temperature. Not as low as we need liquid helium, but it's already rather low. But it has quite a small lattice constant. And so our thought was that maybe the fact that europium titanate is not a ferroelectric and barium titanate is just because of this difference in lattice constant. So here's kind of our, at the moment this is just a hunch, there's no density functional theory in here, but we thought that, well, maybe if we start allying barium into europium titanate, we take out some of the magnetic europium ions and put in barium, maybe our Néel temperature will start going down. Seems pretty likely because we're diluting the magnetic atoms. And maybe at the same time, we'll start to grow in a ferroelectric polarization, because maybe when we start increasing the lattice constant by adding barium, the titanium's now just going to have more space to move and it'll go polar. So this was entirely just kind of solid state chemistry intuition. So before we jumped up and down and tried to persuade someone to try this, we thought we'd better do a density functional calculation and see what happened. And so we picked, because of the ease of creating a reasonably sized supercell, we thought, well, we'll start with the 50-50 alloy. We didn't really have any reason to think that these should intersect at 50-50, but it was just a good place to start. So we did these calculations with Kostyurzhansky and Mariana Lejajic in Jülich, and we made a supercell of europium, barium, titanate. We tried a bunch of kind of different arrangements of europium and barium to try to not pick out kind of anything specific to one symmetry. And we relaxed the structure, and we calculated the polarization. And we got a polarization of 25 microcoulombs per square centimeter, which was really rather a respectable number. The even more exciting thing, remember I said that they need to be able to switch this at very low temperature, which becomes very hard. The coercive fields tend to become very large at low temperature. But what we found was when, in our calculation, we increased the pressure, so we just reduced the lattice constant in the density functional calculation. For rather reasonable values of pressure, the polarization starts to go towards 0. So really our idea of what the physics was, that this is just a lattice constant thing, was correct. So we're sitting kind of in this region and we increase the pressure, we drop the polarization. So this should make it rather easy to switch if we could play with the pressure. We found that the relaxed structure with the polar ferroelectric structure had rather large europium displacements. So this picture, much of this is very helpful, is showing you how much the atoms move from the symmetric structure in the ferroelectric ground set, and the europiums move quite a lot relative to the oxygen. So this was good. We wanted the magnetic ion to be the one that was displacing. And we found as we diluted that the magnetic interactions are very strongly suppressed. So we don't expect magnetic ordering liquid helium. So this was where we were until actually last week. I just was updating this slide today. We worked with the group in Prague that showed an eye in it, of Stanislav Kamba, who had already made europium titanate samples, and he made some ceramics, initially 80% dense, and he now has 95% dense ceramics. And this is his measured dielectric response as a function of temperature. And these curves are for dielectric measurements made at different frequencies. And this peak in the dielectric response here, this divergence, is corresponding to the ferroelectric phase transition in the European bearing calculator. So we do indeed have, well above room temperature, which is what we would expect, a transition to a ferroelectric state. We don't have magnetic measurements yet, but that we're fairly confident about. So we have our sample, and I guess our next step is these are on their way to Yale to try to measure the dipole moment of the electron, and I think if we do it and disprove any of the extensions to the standard model, you probably will hear it from someone other than me. Okay, so some morals. I turned 40 this year, so I feel this entitles me to make philosophical comments to young people. This was quite a scary experience, but it's been fun, you know. They're a little, you know, it was scary, but it was okay. I'm still here. So do it, you know, talk to people in other branches of physics, because they may have problems that you can solve. This was not, for us, the hardest problem in the world to solve, and for them it could save having to build the Large Hadron Collider, you know. So it could be quite significant. And be happy if you get a good result, even if it really wasn't what you were looking for. The bismuth ion chromium was one example. We told the experimentalists not to bother. It wasn't going to be a room temperature multiferroic, and they ignored us, and it was. So I wanted to put this example up. This was another compound we persuaded our experimental colleagues to synthesize. And what is the most striking thing to you about this compound? When you see this compound, what do you think? People at the back. What is going through your head when you see this compound? Blue. Isn't it beautiful? This is the most beautiful blue compound. The search for blue compounds. You shouldn't laugh. The blues and synthetic blues you have at the moment are like cyanides and horrible organic things. Blue was the first synthetic pigments. The Egyptians, there was like whole, you know, trading and cultures based on the fact that they had this Egyptian blue. Then the Chinese took over Han blue, and then the Mayans, Mayan blue. Every significant major culture has developed a new blue pigment. And it's a big deal to get a new blue pigment. We designed, this was our latest designer magnetoelectric. And it has zero magnetoelectric response, but we've just submitted this beautiful paper on the design of blue compounds, and then this is very exciting. So be happy. Well, be happy generally, but be happy if you get anything good, even if it wasn't what you were looking for. So that's it. Go and have a beer and relax. And
were you able to predict the color?
No, in fact, it was really, really hard to even reproduce it afterwards. You know, so we're doing beta sub theta calculations. The darn thing doesn't come out blue in any conventional density function. And it's not. But the reason it's not magnetoelectric is because they put their atoms in the wrong place. It would be if they could arrange it. It needed to be ordered, and they weren't able to order it.
I was able to predict that grass is green.
You were?
Yeah.
With density functional theory?
Yeah.
Maybe we should talk to you then. But green is, you know, blue.
Well, I agree that kind of blue is much nicer than the green I predicted for grass.
But yeah, I don't know if you're discussing this week optical properties at all. Optical properties are really, really hard and very non-standard, and they're not a ground state property, obviously. So we struggled actually with the final version of the paper to figure out if we could do anything at all to justify authorship. You know, we persuaded these guys to make it, and now we're like, oh, you know, we can't even get it to be blue in our calculations. But we were happy because it was pretty. So any other questions? Or Jennifer tells me that the best place in Isla Vista for a beer is Dublin. Did you guys find it yet? Oh, Sinead found it already, of course. Yeah, the Irish. So we can wrap up and you can go.